English captions, please. This is the 6th video on chapter 7, and we will learn to name acids. This is part of chapter 5, the end of chapter 5. So from your textbook, go back to chapter 5. Naming acids is covered there. So acids are molecular, which means also covalent compounds, right? They are made of nonmetals only. But they form ions when they are dissolved in water. Even though they are not ionic, they will behave like if they were ionic. So they are composed of hydrogen, usually written first in their formula, and then one or more nonmetals, written second. We can categorize acids into two groups: the binary acids, so those are containing only hydrogen and one nonmetal, and the oxyacids, and that's the acids that contain hydrogen, a nonmetal, and oxygen. So oxy here refers to oxygen. Acid means you have hydrogen as first in the formula, and then other nonmetals. So if you classify acids in two general categories, acids are molecular compounds that have H as first element in the formula. And then there are the binary acids that contains hydrogen and no oxygen, and the oxyacids that contains hydrogen and then oxygen. And this is typically a polyatomic ion. You will see that oxyacids are made of a polyatomic ion and hydrogen. So let's start by naming binary acids. Binary acids are composed of hydrogen and a nonmetal, and that nonmetal cannot be oxygen. It's always something else than oxygen bonded to hydrogen. The names for binary acids have the following form. You need the prefix hydro to refer to an acid. And then you take the base name of the nonmetal and change the ending to -ic. And then you finish by naming it acid. So the base name for various nonmetals and their common charges in ionic compounds are given here. So fluorine, chlorine, bromine, iodine, all the halogens here have roots that you know already because you have used them for, the fluoride ion, chloride ion, bromide ion, and iodide ion. So acids will also use the nitrogen and the phosphorus and the sulfur. However, for phosphorus and sulfur, the root will be longer. Phosphorus will be phosphoric and sulfur will become sulfuric, not sulfic. But all the others will be used like fluoric, chloric, bromic, iodic, and nitric. So naming binary acids that contain no oxygen. So for example, HCl is a binary acid. It's called hydrochloric acid. So because it's a binary acid, you need the prefix hydro. Then you take the root or the base name of the nonmetal, and here chlorine, so it's chlor, and you change the ending to -ic. So hydrochloric, and you finish with acid. Hydrochloric acid. HBr, so it's made of the bromine. So you take brom and you change the ending to -ic and put hydro in front. So hydrobromic acid. So notice how HCl, when it's the gas, so notice how the two acids on the first part of the slide here are aqueous solutions, right? Acids are always aqueous solutions. Here, HCl, if you have this with a gas, if it's a gas, it refers to the hydrogen monochloride molecules in the gas phase and not to the acid. You see how the name is the name of a molecular compound or covalent compound. You have the name of the first nonmetal and then the prefix mono and then the name of the second nonmetal with the ending -ide. So when it's not in an aqueous solution, HCl is named like that. hydrogen monochloride. But if it's in an aqueous solution, then it becomes dihydrochloric acid. So another example, H2S is hydrosulfuric acid and not hydrosulfic. So even though the sulfur becomes the sulfide ion, here we keep the UR because it's easier to pronounce. So it's sulfuric, not sulfic. So because it's a binary acid, here you have the prefix hydro, hydrosulfuric acid. H3P is hydrophosphoric acid and not hydrophosphic acid. Notice how, again, here the root is a bit longer. It's phosphor and not just phos. Then with the ending ic and the prefix hydro. So hydrophosphoric acid is H3P aqueous. So how do we name oxyacids? So oxyacids are acids that contain oxyanions, and they are found in the table of polyatomic ions. For example, HClO4 aqueous contains the perchlorate ion. ClO4 -1 is the perchlorate ion. And so if you bind it to an H+, it becomes the perchloric acid. H2SO3 aqueous contains the sulfite ion. SO3 -2 is called the sulfite. And so you see that if you combine it with the hydrogen, then you get H2SO3. Another example, H2SO4 contains the sulfate ion SO4 -2. So you need 2 H+ to make it a neutral formula, H2SO4. So these acids are combinations of one or more H+ ions with an oxyanion. And so the number of H+ ion depends on the charge on the oxyanion, so that the formula is always charge neutral. Notice how, the sulfite and sulfate need 2 H+ ions to be making a neutral formula. But the perchlorate has only one negative charge, so only one H+ will be enough to make a neutral formula. So that's the table of the list of polyatomic ion, and that's just the common ones. And notice how most of these ions are oxyanion, which means they are made of oxygen bonded to another nonmetal, like the nitrate, sulfate, phosphate, carbonate, the chlorate, acetate, permanganate, dichromate, chromate, etc. So the only exceptions are maybe the ammonium, the hydroxide. Well, hydroxide is also oxygen and hydrogen together. The cyanide. So these oxyanions, when you combine them with H+ ions, they make oxyacids. So how do we name oxyacids? There are two types of oxyanions, those that end in ate and those that end in ite. If you noticed in the table earlier, I've named all the ones ending in ate, but there is also the same type ending in ite. So that's the most common endings for the polyatomic ion. And so depending if they end in ate or ite, we name them differently to be able to discern them. So the name of the acids containing oxyanions ending with ate will take this form. So you take the base name of the nonmetal or the polyatomic ion, and you change the ending ate to ic and add acid. For example, H2SO4, the SO4 -2 is the sulfate ion. When it's combined with two H+ ions to make a neutral formula, we call this, so you take sulfate, you change the ending to ic. So sulfur, again, remember now becomes sulfur when you name an acid. So from sulfate, it becomes sulfuric acid. And HClO4, for example, we said there was the perchlorate ion in there. ClO4 -1 is the perchlorate. And so you change the ending H to ic, and it becomes the perchloric acid. So we differentiate them from the binary acids because these don't have the prefix hydro. So if your oxyanion has a name that ends in "ite", then the acid will be named like this. You take the base name of the nonmetal or the polyatomic ion, and you change the ending "ite" into "us", and then add the name acid. For example, H2SO3 contains the sulfite ion and then bonded to 2 hydrogens. And so sulfite, you change the ending "ite" into "us". But remember how sulfur, you go back to sulfur, and it's sulfurous acid, H2SO3. HOI, IO or OI -1 is the hypoiodite ion. It has 1 negative charge, so it's bonded to 1 hydrogen when it's the acid. And so you take the name of the polyatomic ion, hypoiodite, change the ending "ite" to "us", and it becomes the hypoiodous acid. So let's go through some examples of writing the formulas from a name. So here we have a name, phosphoric acid and nitrous acid. So phosphoric acid, the fact that there is no prefix hydro tells you it's an oxyacid. The ending "ic" tells you it's made from a polyatomic ion that ends in 8. So, so you take the root phosphor and you change the ending "ic" to 8, and that's the phosphate. So this phosphoric acid is made of the phosphate and then hydrogen. So to find its formula, you take the formula of the phosphate ion, PO4 -3. You place hydrogen in front, H+, and then you do the crisscross trick, and you see that the 3 from the charge of the phosphate will become a subscript for hydrogen, and it's going to be H3PO4. You need 1 phosphate ion and 3 hydrogen ions to make this a neutral formula. So phosphoric acid is H3PO4. Let's look at the second example, nitrous acid. So there is no prefix hydro, so that's an oxyacid. The ending us tells you it comes from the polyatomic ion that ends in "ite. So nitrous comes from nitrite. So let's find the nitrite formula. The nitrite is NO2 -1. If you look at the list of polyatomic ion, that's the one. So nitrite, when it's combining with H+, it will make the nitrous acid. So you place the H+ in front of the nitrite, and you see that one of each ion will make neutral formulas. See if you put them together. So it's going to be HNO2. So the nitrous acid is HNO2. So let's go through a concept check and name or write the formulas for the following acids. So first we have HF, aqueous. So HF, it's only made of hydrogen and fluorine, right? So that tells you it's a binary acid because it's made of just hydrogen and 1 nonmetal, which is not oxygen. So it's a binary acid. And so you will need to use the prefix hydro in front of the root of the nonmetal name. So fluorine is the fluor root. So hydro, fluor, and you place the ending ic, hydrofluoric acid. So HF is the hydrofluoric acid. HiO4 aqueous. So here we see the oxygen and the hydrogen and another nonmetal. So that's an oxyacid. That's an oxyacid, and we need to find the formula of the polyatomic ion. We see that if we remove the H, we have IO4, and that's a polyatomic ion that is named periodate. IO4 -1. The same way we have the perchlorate, perbromate. This is the periodate. It comes from the iodate, which is IO3 -1, with one more oxygen, IO4 -1, then becomes the periodate. So this is an oxyacid, so there's no need for the prefix hydro. So you take the name of the polyatomic ion, periodate, and you change the ending 8 to ic. From 8 it goes to ic, and then add acid. So it becomes the periodic acid. And that's a funny name, right? Periodic acid. Periodic acid. So acetic acid. So that's a name. We need to find the formula. There is no hydro in front, so that's an oxyacid. And it has the acetic name. So the name ending in ic means you have an oxyacid with the ending 8, right? Because ic means it came from a 8 polyatomic ion. So you take acetic, change the ic into 8, and that becomes the acetate. So it's the acetate ion, and the formula of the acetate ion is C2H3O2 -1. If you look at your list of polyatomic ion. So that's the oxyanion, and we need to add to it the H plus in front. So H plus and then C2H3O2 -1. You see we have one positive charge, one negative charge. So one of each ion will make this a neutral formula. So it's going to be H, C2, H3O2. And so notice how we keep the H on purpose in front here to show that it's an acid. And then it also helps us recognize the acetate ion. C2H3O2 is the acetate. So acetic acid is HC2H3O2. Hydrocyanic acid. So here we see the prefix hydro, so that tells us it's a binary acid. So it's a binary acid. However, cyanic is not, or cyan is not a root for an element, non-metal, right? It's not fluorine, bromine, chlorine, sulfur, phosphate, nitrogen. It's not any of those. So you need to find in the list of polyatomic ion what this can be. And cyanic comes from the cyanide, and it's a Cn -1. So it's a special polyatomic ion that's not made with an oxygen. So that's why it's considered a binary acid, because there is no oxygen in there. But it's made of two, it's a polyatomic ion. It's not just one element. So Cn-1 is the anion, and we combine that with H plus to make the acid, and we see that the charges cancel when you have one of each ion. So that's going to be HCN, the hydrocyanic acid formula.